yeah, telling something about bridging hardware and software, namely how to optimize quantum compilation and the benchmarking for what? For scalable quantum systems. So perhaps also our goal is to create scalable quantum systems. And so let's see, to create scalable quantum systems. And I would like to start with some challenges, so to say, as a negative motivation, so to say. So what are some challenges here? We are currently in NISQ era, you know this, and it's fantastic what the people are inventing out there. However, I think to make the technology really useful, we would need to scale up. And this means that we need more qubits and better qubits, even better qubits. And this is an engineering effort. So one of the challenges that we right now have is the qubit itself. We need qubits for quantum computing. There are so many different technologies out there. There's many good candidates with lots of pros and cons. So there are lots of trade-offs. And a quantum computer is more than just qubits. So it is a computer. So we have the qubits, but we also need to steer them. So we have an electronic interface that talks to the qubits, so to say. And let's see if I can make a pointer, laser pointer. Yeah. So oftentimes, or let's say at least here in Delft, it is that in the first floor, we have here these control electronics, and then we have some wires that go down to the fridge to the qubits. And the question now is, how would that scale up? Because you only have a certain amount of cables, so to say, that you could lead into the switch. So how to scale this up? And one of the approaches, one of the challenges is also to head towards cryogenic and integrated electronical interfaces for these large-scale quantum computers. So instead of having here these electronic interfaces as a bulky equipment in room temperature, so to say, the idea would be that you create cryo-electronics that works down there in this temperature regime. So having this in one place as an integrated thing. Well, and a quantum computer is more than just qubits, but also more than qubits plus electronics. You also need a complete overall system architecture. You see, we have qubits, we have the electronics, but you also need to run this. And here I'm thinking about the overall system architecture, like computer architecture in a way. So the basic idea is, if we have an algorithm in mind that we would like to run, how can we bring this algorithm down to the chip? And this is basically what we will talk about today. So about this quantum computer architecture. And let's directly dive into some of those architectures. So why is quantum computing architecture interesting? So here, the main idea is basically, let's not reinvent the wheel. We have, for decades, knowledge of how to build computers, and a quantum computer is also a computer. So perhaps we can learn and reuse some things here. Let's try to build on classical architecture principles, but we cannot recycle everything. So we also need to handle coherence, or rather decoherence, error rates, qubit connectivity, and more. We'll talk about this today many times. And while we tackle the challenges of NISQ devices, I also think that we, at the same time, also aim for large-scale fault-tolerant quantum systems. So basically, here's the completely classical world, and we try to work on these NISQ devices. But in the end, where we would like to head to is this fault-tolerant regime. And these lessons learned today are helpful, in my opinion. And I really find this field so interesting because it combines so many different domains and topics, from theoretical and experimental physics to computer science, computer engineering, electrical engineering, and many more. And this pushes the boundary of computing. And I think literally, because if you see that some company says, yeah, groundbreaking results, and it's classically not simulatable, next day some people will classically simulate this, and I find this funny and interesting and also healthy. So it's kind of a positive arms race. And when speaking of architectures, it's also the case that there's not one single blueprint. So there are so many different cubic technologies. They have diverse layouts and design choices, what we'll talk about today. So there is no one single blueprint. And also architecture and blueprints, they have different details and different goals, what they would like to convey. So sometimes you have some high-level layered architectures, or sometimes it goes really down to the pulse level control schemes. And as always, there is a trade-off. Trade-offs are everywhere. So you cannot crank up any of the knobs and have then the perfect architecture. There are trade-offs. And these then relate to the gate fidelities, qubit connectivities, error correction overhead, and many, many more. And this is what we're talking about today. And yeah, it's so evolving, so we have no single blueprint. Also because the field is so rapidly evolving. So we have so many new proposals all the time and refinements appear regularly. So not yet, we don't have a one-size-fits-all approach. In the classical world, after 50 years, I believe, we have something like this. It's standardized. I mean, we have a notebook from different vendors, and perhaps the CPUs are from different vendors, but it's very, very standardized. And this is still missing in the quantum regime. On a computer architecture can mean different things. So it could be that we mean the topology of the qubits and the possible two-qubit interaction. So for example, this here would mean that qubit 1 can perform a two-qubit interaction with qubit 2 and also with qubit 0, but not, for example, with qubit 15. Or what we could mean with this is that we bring a little bit more semantic in it, that we have what I just described, but a little bit more complicated, that already some notion of error correction is in there, that we have some data qubits, that we have some ancilla qubits. Or if we go even further, so for example, with some ion trap designs, you could say, okay, you qubits, you are ancillary qubits, you are for computation, you are for memory. This is what architecture can mean. You could also say, okay, let's layer it. Let's say we have physical qubits and physical gates, and then we say we have virtual CNOTs. Virtual CNOTs meaning, okay, I would like to have a CNOT between this and this qubit, even though they are not connected, and please, architecture, do something for that. And then we could say, okay, we have logical CNOTs, or some application qubits in a way, so that it's stacked. And this the stacked approach means that we have some abstractions, that a layer abstracts something from below. And it's very similar to classical computing. So we have conventional computer architecture, and basically you just put a Q in front of that and then have a quantum computer architecture, because you have applications and also quantum applications, quantum algorithms, quantum programming languages, etc., etc. So lots of different ways of creating an architecture, and the one that we are mainly using, because it helps us for streamlining our research, but also for teaching, is this one here. And you see at the very top, there are like quantum algorithms, so more the application. And then down there, here you have the quantum chip with the qubits. And yeah, basically today I would like to focus a bit on this part here, the compiler, that in the end bridges the gap between algorithm and chip on a high level. Let's look into this. So on abstract side, you would say that it translate an algorithm into a series of pulses or whatever is needed. So you have an algorithm, you have this algorithm in your mind, and then you could, with some high-level programming language, for example, Python, program this. You bring this into code, you discretize this, and then with the help of a compiler or of a computing architecture, you would create some lower-level instructions, assembly, for example. And this then in turn still gets translated into, for example, a series of pulses. And that's the story. So going from top to bottom and perform the necessary translations. And what most of community is doing for this, they're using multi-pass quantum compilation. So a quantum compiler that consists of several passes. Yeah, and the idea is, what I just said, to bridge high-level algorithms with the physical constraints. So basically, each of these passes handle unique challenges that we face when translating these algorithms into hardware-friendly instructions. We want to coordinate all of these resources, all of these constraints that we have, and we want to ensure that the semantic of the algorithm stays the same, and that we try to maximize the performance. Yeah, and one can group the task like this, these 5 bubbles here, and perform them. But also in different, so this here, like here, decomposition, optimization, scheduling, etc. This is one way to do this. You could also do some of the passes several times. For example, the optimization pass, you could perform several times, but you could also reorder that. But for the sake of explanation, this ordering here is good. So let's have a look into this. Decomposition. So I guess you know the concept of universal gate set. So a universal gate set is a small collection of gates from which any quantum operation, unitary operation, can be constructed. Examples are, for example, Clifford plus T, or there are some other universal gate sets, also in the classical world, right? And why this matters is the universality of this universal gate set guarantees that we can implement any algorithm up to a certain accuracy. And it also serves as an intermediate language before we are getting hardware-specific constraints into the game. So for example, if we so this part of the decomposition. So for example, if we have a Toffoli gate, and then we are looking at the capabilities of our machine, and then we would translate and decompose this Toffoli gate into this long range of gates here. And this is then still universal, but more tailored to the hardware. And this is only the first step of this decomposition, because then we would go from universal to physical. So perhaps our quantum hardware only supports a different and often smaller set of primitive gates, perhaps some specific single qubit rotations, perhaps some specific 2-qubit gates. So basically, we translate from an arbitrary gate set to a specific universal gate set, and then to a specific primitive gate set of our machine. That's, yeah, extra primitives that the machine understands. For example, I would like to have a swap. The swap could be decomposed as 3 C-nodes, but perhaps C-nodes are perhaps we don't want to decompose it as 3 C-nodes, but as Hadamard CZ plus Hadamard, depending on the native gate set of the chip. And you also see that this opens up some possibility. Basically, we decompose our circuit into kind of the same, from a logic point of view, the same circuit, but with more gates. And now we have the possibility to optimize like this. So you know, quantum hardware is limited in many aspects, like qubit count, gate fidelity, coherence time. So let's make the most efficient use of these resources. And it can be this is really high level. It can be that we try to figure out repeating patterns in our circuit. That, for example, we have two X rotations, and these would cancel out, or we have two different X rotations or some rotations, and then we could just append them, concatenate them. So instead of two rotations, we do one, namely as the sum, and many, many more. And optimizing leads then to the question, okay, but what is the fitness function? And here, it opens up again. So there is not one fitness function. So there are so many different optimization metrics. This is just a couple of examples. So you could say, okay, reduce the amount of gates, or reduce the gates such that the depth of the circuit is as small as possible. Or perhaps we could say, perhaps we can reuse qubits such that we decrease the number of qubits needed, or we focus on specific gates that we are not good at, that are expensive, for example. It's or last example here, overall execution time. So there are many, many different optimization metrics that you can focus on. So after the decomposition and perhaps some initial optimization, it's time to arrange our actions in time. So basically scheduling. And here the idea is that the general idea is that if you decrease the depth, so the lower the depth, the less noise you have. Like, yeah. So the idea would be to parallelize independent gates and to schedule, and the scheduling reduces the total circuit time, and by this it mitigates decoherence effects. So we squeeze it in time. But then, as often the case with trade-offs, this might not be the best idea, because then some other effects might happen, like for example a crosstalk. But for now, let's say we want to lower the depth. But we also need to take into account that the algorithm, of course, has some logic. So we need to respect the dependencies and the timings. So no gates execute before its prerequisites. We account for different gate durations, for measurement delays, for some restricted hardware. And yeah, goal is to minimize idle qubit times, to cut error accumulation, and in the end and eventually to boost the success probability of our computation. Quick example, it might be that we have an input of a circuit. This is just some random circuit, be it as an assembly file or be it in this graph notation here. And we say, okay, good, thank you. This is the circuit we would like to run. We now need to figure out what are the dependencies. And you could then create such an instruction dependency graph. If you look, for example, here at this vertex here, this means that the Hadamard on qubit 2, so this gate here, needs to be performed before the CNOT 2.6, 2.3, and 2.4 are performed. So here, this Hadamard here needs to be performed before these three CNOTs. But between these three CNOTs, there's no dependency. Doesn't matter if you do first 2.6 or 2.3. So this is why there's no line in between. So this is called a dependency graph. And based on this dependency graph, you can then create some scheduling, some time slotting. So for example, you say, okay, Hadamard on qubit 0, 1, and 2 at the same time, and also qubit 3 and 4, the CNOT here. You could also do this at the same time. Note that this is, because we have not too much time in this presentation today, so that this does not take into account, for example, different timings. So for example, perhaps the CNOT or the Hadamard take different durations. But anyways, this is already a first step. We say, okay, this is one time step, this is one time step, etc. And after creating and arranging a little bit in time, we would also arrange a little bit in space, call it mapping. So the idea here is that we have in our hardware, in our topology, we have some constraints. Not all qubits are interconnected to each other. So let's somehow arrange that the qubits that should act with each other can physically indeed act with each other. And if this is not possible, then let's route around the quantum information, like performing some swaps, or so swapping the quantum information or moving it otherwise. But this, of course, nothing is for free, would introduce errors. Yeah? Each swap would add some gates, would add some errors. So let's try to minimize and cut away unnecessary movements. How would it look like? So let's say we have the scheduled the scheduled circuit from before on the left-hand side. And let's say we have a topology that looks like this. So we have 1, 2, 3, 4, 5, 6, 7 qubits, and they can interact when there is an error in between. And then you would say, okay, which of these seven qubits here from our circuit would be placed where on our topology? This is called initial mapping, or some people say initial layout. And let's say I am choosing for this layout. This is a heuristic. This is the Sebastian heuristic. I just want it exactly like this. You also feel that there's a combinatorial optimization problem in there. But let's say I would like to have this mapping here. And single qubit interactions can be performed. And then let's have a look at the first 2 qubit interaction between qubit 3 and 4. And we see that there is a physical connection, and we can perform this. C0 3, 5 is possible, but then we already run into a problem. So qubit 2 and 4 are not directly connected. So we cannot perform a direct C0 between those. An idea would now be to create a swap. We would swap the quantum information of qubit 0 and 2, meaning we swap the information. And now the information of our qubit 2 here lies here in the middle. And all of a sudden we can perform the C0 between 2 and 4, like this. So this is the general idea of the initial mapping and the routing. And what you also see is that after performing this swap here, we change the state. So imagine we have a large circuit in terms of qubits, but also in terms of gates. Then after, I don't know, a couple of swaps, nothing is there like before. So this initial mapping also needs to look a bit into the future, so to say. And I did not even speak about the quality of some edges. So perhaps this 2 qubit interaction here is worse than that one. So there are many things to consider. Good. And what what the compiler also then does is, and that's on a whole other level, and I only have one slide on this with me. It should and could also think about this fault-tolerant synthesis, basically quantum error correction. So we have physical qubits, and the idea is that we encode our logical qubit onto several physical qubits. We spread the information such that it's in space spread, so to say. And if then one of the physical qubit fails, we can still reconstruct the information. That's the basic idea. And meaning we would not have physical qubits anymore, but logical qubits. Also meaning we don't have any more physical operations, but logical operations. And how to keep track of this, how to do this, is also part then of this compilation. And all what I just told you with the mapping and the routing, etc., is needs to be considered here under the umbrella of error correction as well. So lots of stuff going on in the compiler. And I find it super interesting because there are hard problems in there. It scales badly, but we would like to scale because of the fact that we like to have large quantum computation. So there's many research going on, and I would like to show you some examples. Let's look at some practical examples. One of them is, we call it architectural exploration of spin qubit arrays. So there's a technology where you have a 2D quantum dot array. So here, this is the 2D array of quantum dots. And then you have electron spins, here in green, that encode the qubit state. And yeah, this is a schematic representation. And then you have some control lines and readout lines that connect the qubit grid to the outside electronics for control and readout. And as you can see, half of the dots are occupied with a single electron. And you can indeed shuttle these electrons around via gate voltages, and then to couple them to nearest neighbors for a 2-qubit logic gate or for readout. And this is the cartoon version, but still it helps to understand what problems we have here or what challenges do we face. And what we are asking ourselves is, what factors are influencing the QPU performance? Because performance is more than just quantity and quality of qubits. Like if there's then a company that says, yeah, we have 100 qubits, and then there is another company that says we have 150 qubits. This is not the full story. It's about quantity and quality of qubits, yes, but also it's important how the qubits can be operated on the device and how the quantum circuits are mapped onto the device. And there are also non-trivial architectural trade-offs to be made. Like I said earlier, you cannot just crank up everything. And this is what we wanted to investigate. And here in particular, we were looking into some mapping challenges of this crossbar architecture, how it's called. And you see, it is very much constrained on what you can do due to these control lines and the readout lines. There are very strict pulse durations for the operations. Then you have some rotation schemes that I show you in the next slides that are very unique to this technology, gives you opportunities, but also gives you some constraints. You can route physically the qubits, so not only the information, but really physically the electron. And this allows for some parallelization if you do this carefully. But you also have some constraints. So for example, if you do not swap the information, but really move the qubits, then it might be that you want to perform a 2-qubit interaction between this and this qubit, but you cannot move the qubit there because it is blocked. So you need to take care of this. Or there are some parallelization possibilities, but if you do these parallelization opportunities, you need to make sure that you don't have some unwanted interaction. Like I said, some pros and cons. There are then some design choices of, for example, how you implement some single qubit gates. You can, for example, think of that there might be the possibility that you perform that you can only perform some operation on all qubits or on a specific subset of the qubits, or really individually. And this knowledge opens up possibilities, but also increases the search space that the compiler needs to work on. Or there are some techniques of performing some shuttles, and these shuttles can be used for parallelizing stuff. So again, some examples for potential benefit, but also for computational overhead. And the idea is now to investigate if there is some beneficial behavior for when we run algorithms and when scaling this up. So we have lots of design choices, not only number of qubits, lots of design choices from the technical side. How would this benefit the running of algorithms? And what we then did was we created a compiler exactly for this. We called it SpinQ, Compilation Strategies for Scalable Spin-Qubit Architectures. And we also needed a routing algorithm for that. We call it bsnake. Oops, because I told you that sometimes you can have blocked paths, and then you need to move some other stuff out of the way, but perhaps their way is also blocked. So this is then some difficult task, and we had these tools, and with this we were able now to input some circuits into the compiler. The compiler does some decomposition for the spin qubit architecture, the initial placement, and then the routing and the scheduling. And the compiler, of course, needs a target it compiles to. So we had lots of architectural configurations, some of which I just pitched to you. And then it pops out a circuit. We will verify if the circuit basically is, from a semantic point of view, the same as the inputted circuit. And we then have some metrics with which we can evaluate, let's say, the overhead. And we did this by hand, and we said, okay, let's have a look. What happens if we have this and this architectural configuration? And then we looked at the metrics. But by doing by hand is, of course, not the best. So what we did is we made a so-called artificial architect with which we wanted to automate the design space exploration. So basically, we have, again, as an input, lots of circuits, then the design space, so the configurations. We have several optimizers like genetic algorithms and many other optimizers, and some termination condition. We put this into this ART-A, and the ART-A uses then the spin Q and checks what happens, automatically checks what happens with certain configurations. And with this, we can then make some statements. I don't want to go into the details of like the actual values, and but only give you some notions, some flavor of what kind of statements we can make. So basically, what we saw is from an algorithmic point of view, it's super important that the decoherence errors are reduced. Like reduce the decoherence errors at all costs. In our experiments, we found that crosstalk effects are not as strong as we believed. If we have the choice, if we can make a wish towards the experimentalists, we would like to have the possibility to parallelize single qubit gates rather than 2 qubit gates. Of course, parallelizing everything is the best, yeah. But if we need to choose, then this one. Yeah. So this is the kind of statements we were able to make. And we continued this a little bit towards the use of multipartite maximally entangled states. This got recently accepted in PRX Quantum. So here the idea is that generating AME states on noisy quantum devices is super challenging and kind of a stress test for the entanglement capabilities. They're also interesting because they're related to some quantum error correction codes. And they're also interesting because they make use of the full processor, so to say. And here we did the same, so to say. We said, okay, what if we have a bilinear array with some diagonals and with crosses? And then we investigated the effect of the entanglement spread. So long story short, this is our idea of kind of hardware-software co-design. If the people would talk to each other and say, okay, Sebastian, you algorithm guy, if we should focus on something, what would you prefer? And then from an application point of view, I could say, if I can show this, most beneficial for us would be this and this. Or we could also say, yeah, these improvements are good, but from an algorithm point of view, not so interesting compared to this and that. Okay, so this basically, what I just showed you was, okay, what is the effect of the quantum chip on the compilation overhead? And I have now another example with me where we do this the other way around. what effect does the quantum algorithm have on the compiler? Yeah, so same idea, similar idea, but with a shifted focus. Here we mainly looked at superconducting qubit topologies. Here we assumed a fixed topology. We said, okay, we have a computer, quantum computer, this is the topology, be it as a grid here, or this heavy hex, or some other topology. And what we then did was we basically characterized quantum benchmarks in order with a goal to improve the quantum circuit mapping or the compilation in general. So we profiled quantum circuits based on some structural parameters. We found that benchmarks, so quantum circuits that are used as benchmarks, are often not representative. So there's a complete set of benchmarks and in particular performance metrics missing. And what I mean here is, if, for example, you have a circuit, if you have, for example, two circuits, and these two circuits have the same number of qubits and the same ratio of two qubit interactions compared to single qubit interactions. This does not mean that their interaction graph look the same. They can look very different. What is an interaction graph? So basically, you take the circuit, and all of the qubits are a vertex. And if there's a two qubit interaction between a qubit, then this is an edge. And if you look at some structured algorithms, they have then a different interaction graph as a random circuit. And this is what we wanted to investigate. So we wanted to profile and compare benchmarks, not only with standard parameters that you find in the literature, such as the number of gates, circuit depth, etc. This is standard. We wanted to also include the interaction graph and the dependency graph. And here we relied on some metrics from graph theory. And in general, our goal was to make an algorithm-based compilation, focus on algorithms. For this, we tried to make a benchmark collection. We called it QBench, where there were some, and we categorized them. So we said, okay, we have some benchmarks from with real circuits based on real algorithms like QFT Grovers, etc. From some libraries with some reversible circuits, but also some synthetic ones like random algorithms, but also some volumetric circuits that are, I mean, kind of they are real, but they don't solve a problem. They are there for benchmark. So long story short, we created a large benchmark collection. And then how was the approach for our circuit characterization? Yeah, we transformed the circuits into a set of parameters. For example, number of gates, percentage of two qubit gates, and many, many more. We also included parameters for the interaction graph and the gate dependency graph. Graph theory, clicks, max click, bit treeness, diameter, hop count, clustering coefficient, and many, many more. And then we investigated the effect of that on the compilation, if we can see some structure. So basically, we performed clustering. First, we performed clustering only on size parameters. So here on the top, you see, so each of these lines is a circuit. So for example, this particular circuit here has this amount of qubits and this amount of gates and this amount of two qubit gate percentage, etc. So we first clustered our circuits based on size parameters. And then inside of these clusters, we then continued in a bit more fine-grained approach to have a look what happens regarding these graph parameters. And what we then found is that, here on the left-hand side, you see different colors are groups of benchmarks based on their origin. And then you see something like that random circuits, for example, have another overhead than circuits with a proven speed up. Or here, we looked into one group, and then we showed the gate overhead in the color. And then we see, for example, that the number of qubits and 2-qubit gate percentage has a higher influence on the gate overhead than the number of gates. See, that's going from yellow to red and black. Or on the right-hand side, you see that the fidelity decrease on the same circuits. And then, unfortunately, and kind of, what was to be seen is the higher the parameters, the worse the fidelity. So we have many, many plots of this. But what I wanted to say is looking deeper into the circuits can give you an estimate on what will happen after the compilation. And then just to have named it, we also did this for multi-core computation. So basically the idea is you have a circuit, you can run it on a single core, or you can cut it and then lay it on multiple smaller cores that are sparsely connected. This is what we also investigated together with groups in Valencia and Barcelona. Okay. And perhaps then the last example is about realistic and realistically looking benchmarks. Why do we need realistically looking circuits? What we found is that it doesn't matter what this means, but I just want to show that blue and orange are different. What we found in all our compilation research is that real algorithms and random algorithms perform differently. You see this already visually, that QAOA, the interaction graph, looks different than a random circuit interaction graph. So basically, we need lots of realistic circuits to perform the benchmarking of devices and of compilation. But I would also like to train reinforcement learning agents to perform compilation. What we did is we made a software tool that is called QGIM. It's a GIM for training and benchmarking reinforcement learning based quantum compilation, really like OpenAI's Gymnasium, but for quantum compilation. And to train reinforcement learning, you need lots of data. And the idea was now, perhaps you know this websites, this person does not exist, this cat does not exist. You know, so some diffusion models, some transformer-based models, some GAN models that create realistically looking things. So I thought I would like to have this quantum circuit does not exist. Yeah, and idea 2, yeah, let's do it. Transformer architecture. ChatGPT means generative pre-trained transformer. And the goal of ChatGPT is to create realistically looking text. And the idea was now, could this be used for quantum computing? Can transformer models be used to generate realistic looking quantum circuits to expand our quantum algorithm data sets? And what do we mean with quantum algorithm data set? Yeah, look at this. Look at this arbitrary assembly snippet here. What you see is that there is structure. This is text, and there's structure in there. You see we have a Hadamard on a certain qubit. You see that we have Hadamard on qubit 0, qubit 1, qubit 2, qubit 3, qubit 4. So there's also some ordering. A human being would never, what means never, but would not do a Hadamard on qubit 3, then on qubit 0. So there's a structure in it. And you also see then here some rotations in a certain style, CP, CX, CP, CX. So realistic circuits have some features. Like I said, numbers in ascending order, some repeating elements. And this is what we wanted to learn. So and I think I'm running out of time. So we created ChatGPT, yeah, like ChatGPT but for quantum circuits, ChatGPT. And with this, we are now able to create more realistically looking circuits. You can have a look into this paper if you like. And just to give you an exemplary result, ChatGPT provided us with this here. So Hadamard on qubit 0, Hadamard on qubit 1, CZ, Hadamard on qubit 2, 3, ZZ, 4, 5. You see there's some structure in this. Lots of CZs. And this resembles more to a real algorithm as a random algorithm. I could talk for hours about this. It's really difficult also how to evaluate that this is good. And no, it does not solve any problem. It's realistically looking. Yeah, it's some gibberish, but the structure is in there. Yeah, and like I said, I want to use this QBench and then our ChatGPT to create a large set of realistic circuits. With this, we want to feed it into QGen to train an agent to implement this then in a quantum compiler. Yeah. So to conclude, I think this whole topic bridges disciplines. So we are on a journey towards scalable quantum computing. It demands a tight integration of hardware innovations and sophisticated software techniques. Multipass quantum compilation is a way to minimize errors, to maximize the resource utilization. Benchmarking and having lots of data is crucial for learning, for training, for benchmarking. We want to have a robust system. And I think that what we are doing right now, together with physics, computer science, engineering, it pushes the boundaries of what is possible. What I earlier said with, okay, some people claim this is not classically to be simulated. The next day, someone simulates this. And I'm pretty sure that refining current technologies also paves the way then for fault-tolerant quantum systems. We learn on our way. Okay, and basically with this, I would like to acknowledge my team. This is really great work, what they are doing, so I'm really proud of them. I would like thank them, and I would like to thank you, the audience, and I'm open for any question that you might have. Thank you.
Yeah, thank you so much. That's a really great talk. I mean, pretty interesting topic and pretty informative lecture. Any questions from audience? You can feel free to unmute yourself or just directly tap in the chat box. Yep. I see someone raised a hand. Yeah.
Hi, nice to meet you, Sebastian. So thank you for this amazing talk. And I have a question related to your paper, the interaction graph-based characterization of quantum benchmarks for improving quantum circuit mapping techniques. So I like it very much because two of my works are inspired on this interaction graph-based approach. So my question would be that is it any opportunity for this interaction graph-based idea to be applied into the fault-tolerant synthesis?
Yes. So yeah, so thank you very much, and I'm happy that you liked it. And yes, it is a topic to on how to investigate how the interaction graph characteristics and the dependency characteristics, how they relate to error correction. So I completely excluded this today. So if, for example, you think of just a plain surface code, you encode your logical qubit on the physical qubits with lots of ancilla qubits. Then you have the stabilizer measurements. You have these CNOT dance. So these stabilizer measurements are done all the time. And then you would like to have a fault tolerant CNOT, for example. And then you, depending on which scheme in the surface code you're using, you need to implement this. And here it's the same question, but on another level. So earlier we asked, okay, what effect does the physical interaction graph have on the physical qubits? And now it's the same question, but on a higher level. What effect has the logical interaction graph on the logical qubits that are made out of physical qubits? And we, in this PhD thesis, we explicitly excluded this. We did not take care of this. But all of the questions can be researched in this regime as well. Yeah.
Okay, thank you. Yeah.
Thank you.
Any other questions? So probably I can ask another question. That's not, since Xiangyu already asked the technical detail, I would like to inquire about your perspective of recent topic of the like how to using the high performance computing to assist for example, the quantum compilation. Would you think that could be very promising, very helpful?
High performance computing, you mean?
Yeah, HPC.
Yeah, HPC. Yeah, so this is a very good question. So on one hand, all this compilation is tricky. It explodes, and it's a really complex task. And the idea could now be to use a high performance computer to solve this task. However, the recent algorithms or the recent usage of the quantum computer is more in a hybrid way. It's more in a variational way, such that we can most often not have a circuit, we compile it, and then we run it. It's more this interactive approach. And here the people are very much investigating on how to make the HPC supercomputer so somehow very near to the quantum computer. One idea, of course, because a quantum computer is also an accelerator, so the people are right now placing a quantum computer really in the facilities of the high performance computing building. This is one idea, but how to make it really answering very fast without latency. This is a question that I think has not been solved nowadays. And like I said, right now the algorithms are more that they need to be compiled iteratively in an interactive way, so to say. And then there's also a thing that there's the possibility, for example, or the idea of having mid-circuit measurements, depending on the results, doing then something. So, for example, repeat until success. And then after we have the success, after some condition has been fulfilled, do some specific parts of your circuit. And all this makes the integration with HPC very much complicated. So super interesting research topic, many open questions there.
I see. Yeah, I mean, I believe since last year, the supercomputing, the SC conference at Atlanta, there's really a lot of quantum computing related topic. And I believe also NVIDIA attract a lot of attentions in this part of the like quantum computing research direction. So that's the reason why I ask this. I'll ask your perspective for this this direction. Thank you so much.
Thank you.
Yeah, and any more questions? We can probably take one more question, and if there's no more questions, I believe like we can end up here for today's lecture. And yeah, thanks again for Dr. Field for today's pretty great lecture. And just one more question: do you mind us to upload this recording to our website and YouTube?
That's fine with me, yes.
Okay, thank you so much, and have a nice day. Hope to see all the audience in the next lecture.
Thank you so much. Thank you for
Bye
attending. Thanks for
bye.
inviting me.
Yeah.
Goodbye. Thank you.
Thank you.